Ladies and gentlemen, welcome to WiSE, Women in Science and Engineering. This is a program at BCC that has just been started this semester. It is a program open to all students. It is committed to the recruitment, retention, and advancement of underrepresented groups pursuing careers in science and engineering. The Women in Science and Engineering program will have seminars, just like the one you're attending right now, as well as workshops on careers, resume building, graduate schools, networking for future schools and employment, local excursions, career mentoring, and undergraduate research. We have Dr. Julie Sutton today visiting us from the Florida State College at Jacksonville, who's going to talk about DNA analysis in crime laboratories. Our seminars are on the third Thursday of each month at 3 p.m. right here in Building 4 on the Melbourne campus. Our next seminar is Thursday, March 15th. Ann Spellman, who's a marine mammal biologist for the Florida Fish and Wildlife Conservation Commission. Her talk will be on marine mammal strandings, rescues, and research. And on Thursday, April 19th, we have two female engineers from the city of Melbourne who are going to do a joint talk. Each of our seminar speakers will tell you about their field, their accomplishments, and their advice for students pursuing careers in science and engineering. If you are interested in more information about the WiSE program, our website is www.brevardcc.edu/WiSE. That's WISE. There are also blue sheets going around with a pen for you to put down your name and email, and I will contact you with more information about our upcoming programs, as well as being listed on our website. My name is Dr. Ashley Spring. I am a biology professor here at BCC, and Dr. Mary Ross-Lanowski, who you talked to when you first entered, who is our assistant provost here at BCC Melbourne, and we are your contact people for WiSE at BCC. Without further ado, I would like to introduce our speaker today. This is our guest, Dr. Julie Sutton, and she is going to tell you more about DNA at crime scene labs.
Thank you. As you can probably tell by my fine Australian accent, I'm not from around here. I did actually move here about 10 years ago, and I'm guessing I'm probably one of the few people in the room who actually had to move north to live in the south. Usually what I like to do is start off so that you will kind of understand if you are asking a question and I give you a somewhat odd answer, why that might be. The first time that I actually went to a supermarket here in the United States was actually quite a traumatic experience for me as an Australian. I managed to get into the supermarket all fine and well, and I managed to wander up and down the aisles fine and well, and I managed to get all my goods and chattels and get them into what I would call a trolley, which I believe you guys call a wagon or something or other else. And I managed to make my way finally down to the cashier. And so I was standing there, and I was just absolutely mesmerized by all the candy and magazines and stuff that you have, at the checkout. So, of course, I'm not really paying a great deal of attention. I'm kind of sitting there, with my wallet, which is, usually fairly messy, and I'm just looking through it. And in the dim, dark recesses, I sort of hear this little voice, "Ma'am, paper or plastic?" And I think, oh, okay, not talking to me. I don't have any paper or plastic, couldn't be anything to do with me. And then I wait for a bit, and people start looking at me, and then I hear in a little louder voice, "Ma'am, paper or plastic?" And I'm just stunned. It's like, I have no idea what you're asking me. I don't know what's going on. And I look down at my wallet and I go, "Paper, I'm paying with cash." And so, yes, everybody laughed. Unfortunately, in Australia, if you go through the checkout, your groceries kind of just get shot down the end of the aisle, and you're up to your own devices as to whether or not how you pack them or whether you use paper or plastic. I now know that paper or plastic refers to the bag. So the point of that story is if you should ask something and I give you an off-the-wall answer, it's probably because I just plain don't understand what you're talking about, and that would be a me thing and not a you thing. Okay, so just out of interest, how many people here actually watch CSI? Yeah, a fair few. And how many people love it? Okay, any forensic scientists here? No, okay. Usually when you ask that to a room of forensic scientists, very few people put their hands up, and when you ask whether or not they like it, most forensic scientists don't like it. The reason possibly why is we lovingly refer to it in the business as actually crime scene inaccuracies, because it's made for television, it's made for drama, it's a great drama series, it's well written, but there are certain inaccuracies, and I would suspect that irrespective of what show was being made, any particular expert would probably criticise a show that was made on their particular field of expertise. So the first thing I wanted to go through is why, for forensic scientists, we think that this should be called crime scene inaccuracies. There are a number of things that we find somewhat odd about it. The first is the scene, followed by the clothing, followed by the workplace, and then the turnaround time. Now, usually the scene, you will see, beautiful sunny days, people walk up to the scene, they're dressed very nicely, it's all good. I can assure you that's so totally far removed from reality. The first scene that I ever actually went to was a fire scene, an arson scene. And this was back in Canberra when I was working for the Australian Federal Police. Now, Canberra has the extremes of temperature. Probably the weather is more similar to places like New Mexico, maybe Albuquerque or somewhere like that. So you have hot and dry and cold and dry. And I started in January, which in the Southern Hemisphere is summer. So you can imagine, we're in a burnt-out house. The house is all blackened. There's no air conditioning. It is stinking hot. We're dressed in our overalls, and we have to shovel out great gobs of burnt residue into buckets and take those back to the lab for analysis. That was the first scene that I ever actually went to. I was actually employed at the time as a lab person, certainly not a scene examiner. And at that point, I realized how lucky I was to be a lab person, that I would never have to do this again. The next thing, which is totally unrealistic, is the clothing. Now look how nicely they're dressed. Now take one look at my clothing. I've dressed this way deliberately. This is a typical sort of crime scene outfit or a lab outfit. You've got, the good old polo shirt, cargo pants, lots of pockets. Pockets are really important. You want pens, you want tape measures, you want all sorts of things, labels, and you need to have them readily handy when you're going to a scene. I've never actually seen anybody go out to a crime scene like that, unless it was the boss who was bringing the pizza for the meal break. This type of clothing that you see here would typically be reserved for going to court, or maybe if you had a meeting or a job interview and you want to impress somebody. So if you're actually going for a job in forensic science, wear this. But if you're doing the job, this is what you look like. Okay, the workplace. Have you ever noticed when you actually watch one of those shows and you look at the workplace, like particularly the lab, you look at the lighting in the lab, have you noticed how dim and dark it is? You can't see squat. Like it kind of looks almost like the lighting up in the back of this auditorium. That is also totally unrealistic. We'd never be able to find anything if we worked in that type of environment. This is just a shot of a couple of analysts working in the lab from CSI. I liked it because it said Julie Consult. Occasionally we actually do that. We do actually work in teams quite often. We do actually have some consultation. It would be rare that you would wear any sort of dark blue clothing in a lab, and I'll go into a few reasons as to why later on down the track. You actually want to make sure that you have white cotton lab coats. Some of the other things that you might do when you're actually in the lab, you do actually conduct briefings. I thought this was quite amusing. For those of you in the room who hopefully are not colourblind, you'll notice that this looks like a shirt and it looks like the person has fallen into a vat of Jello. I don't think I've ever seen a briefing done that way. You might take photographs of an actual item of clothing. It's rare that you will do a mock-up like this. This is what it actually looks like in the lab. You notice nice and bright, lots of light, people in white coats, and occasionally we do consultations. Okay, so that gives you a bit of an idea about the actual workplace and the clothing that we'll wear, the type of scenes, and finally the last thing I want to go on to before I move on to what you actually need to do to become a forensic scientist is the turnaround time. Now, for those of you who watch CSI, all crimes are solved in what period of time? 1 hour. Exactly. That never happens. It's depending on the severity of the case. Best turnaround time you could probably get might be 2 to 3 days. More realistic turnaround times are of the order of, weeks. So probably 6 weeks is pretty fast if you can turn something around in that time. Okay, people often ask, what do I have to do to actually be a forensic scientist? And there are a number of different things that we actually look for in forensic science, first being qualifications. Nowadays, it would be pretty rare for you to enter the field of forensic science without at least a 4-year degree. Depending on the field that you actually want to go into, you may need further postgraduate studies after that. For example, I think the field that has the highest qualification requirement is actually toxicology. To work there, you actually need a PhD in either pharmacology, you need to be an MD, have a tox background, something like that, or you might be able to get into, toxicology if you also had, say, PhD in chemistry or something like that, some type of related field. DNA, on the other hand, they will take you with a 4-year degree. However, you are required to have certain credits in certain areas, and the required areas are biochemistry, molecular biology, genetics, or statistics, something like that. If you want to actually be in charge of a lab, then you need at least a master's to be able to do that. Other sort of areas such as, say, firearms and ballistics or fingerprints, document examination, typically those sort of fields that are traditionally police sciences, those usually require a 4-year degree. Next thing they look at is background checks. Nothing is sacred with respect to the background check. They want to know all about your nearest and dearest, so all about your family members. They want to know who you associate with, so they want to know who your friends are. They also want to know who your neighbours are. They want to know what clubs and hobbies, clubs you belong to, hobbies you're interested in, what do you do in your spare time. They also like to know about your financial background. In Australia, they will also ask for your financial records from your spouse as well. And in Australia, they also want to know about your sexual partners as well. A lot of people in the United States have really rolled over backwards when they found out that we actually get asked these questions in Australia. The rationale behind it is that they don't really know what your answers are. What they're looking for is whether or not you're going to tell the truth. The reason being, if you are hiding something, then you become a liability to the organisation. You have something that somebody can blackmail you with. So hence, that's why the interest. The other thing that you are required to submit to, assuming you get through all of this, and eventually you get to an interview and they decide that they will hire you, then finally they want to look at some metrics, which usually involves fingerprint check and also provision of a DNA swab, and they will normally run that against the criminal database to want to make sure that you don't have some crime out there in the ether that you have committed in the past, and they're actually letting the perpetrator into crime lab. Okay, so what does a forensic scientist do? Well, there are a great many different fields and specializations. Unlike CSI, you don't have one person who actually comes to the scene, collects all the evidence, runs it through the equipment, scientific equipment, and then comes out with a result and presents it in court. Usually what you have is a crime scene specialist. That person is specialized in collecting the evidence, looking for things that may be out of place, and then that person will farm that evidence out to each of the specialists. And it depends on what type of case it is as to what kind of specialist is going to be involved. So, for example, if it was something like a fraud case or writing bad checks, then obviously that would probably go to a fingerprint person and maybe a document examiner. If it were, say, a case that involved property damage, then that would normally go to a criminalistic specialist. So they might be looking for something like tool marks, or they may be looking for paint samples, or they may be looking for chemical residues or glass fragments, something like that. If you have a crime and it is against the person, so things like assault, sexual assault, murder, then that's going to bring in your forensic biologist. So usually what I say to people is if you want to go into forensic science and you really like CSI, the TV show, see if you can do some type of internship with either a forensic lab or your local police force and get some exposure so you can see what the different groups do, what the different specialists actually do, and then you can decide what you would like to pursue. Okay, after you've decided what your field of specialisation is going to be, then you have your initial training. This is on top of your 4-year degree. For somebody like a forensic biologist, normally the minimum amount of time that it takes to train you before we would let you loose on any evidence by yourself would be 6 months. Roughly it is a range, usually from 6 months to 12 months. It's usually competency-based, which means there are a number of tests that you have to perform and you have to pass them in order to be deemed competent and then allowed to examine evidence. Once you've actually got past that stage and you're now a fully fledged analyst and able to examine exhibits and present that evidence in court, then we expect you to have continuing education. This is why it's a competency-based system. You could learn something 20 years ago, but if you don't bother to keep up to date with all the new knowledge that is coming out, then you may not be aware of limitations of a particular technique or how the field has moved on and how there may be something that is much better that you could be using instead of your standard run-of-the-mill type test. You're also proficiency tested for DNA analysts. It's at least twice a year. Other specialties, it's at least once a year. These are blind proficiency tests where samples are provided by an external provider. You don't know what the answers are. You have to do the test, submit the test, and you hope and pray that you get the thing right, because if you don't get it right, then usually you get pulled off casework and there is a whole retraining process that you need to go through. Finally, once you've gone through all of that, then you get to do the good stuff, which is actually working on cases, which is more interesting. One of the things that people often don't realise in a forensic lab that there is an inordinate amount of paperwork. I remember when I first joined the Federal Police, I used to joke and say, I joined the police clerical branch because we were constantly writing up files and files and files and files and pieces of paper all over the place and trying to keep track of things. Now, typically, this isn't actually a case file that I have here. It's just my usual laundry list of papers. But typically a burglary case file, it could be about that thick. Anything for a sexual assault or a murder could be something like a D-ring folder full of documents of about 4 inches thick. So that's how much paperwork that you actually have to handle when you're examining or working a case. To give you an idea of the volume of paperwork, you could be carrying, say, 30 cases a month. So you've got 30 of these things that get rolled over from month to month to month. Okay, then you actually get to work the case. That's the fun part of it, where you actually examine the items. So you're spending the time in the lab, you're actually looking for things, you're testing things. Then you get to collate the results, which also is exceedingly time-consuming. You get to write the report. The report is very important. You have to make sure that when you write the report that you disclose the limitations of the test, that you don't overstate the evidence or the weight of the evidence. And then finally, you get to give expert testimony, where you do actually get to wear some nice clothes. But quite often, in that particular case, giving expert testimony, you have to remember in an adversarial society, like Australia or the United States or the UK for that matter, your attorneys have a job to do, and they're basically trying to win their case for their client. So you are probably going to be verbally attacked. You may or you may not be, depending on how strong your evidence is and how damning it is to one side or the other. But you need to be fairly thick-skinned, and you are not able to react. So they can yell at you, you can't yell at them. They can be very angry with you, you can't be angry with them. You just have to remain deadpan the entire time. And that takes a little bit of training. But after you've given evidence for a couple of times, you kind of just get used to it, and it's pretty much part of the course. The one thing that you must have as a forensic scientist is attention to detail. You must absolutely, positively have that attention to detail. The one thing that you will be criticised on in court is if you fail to detect something that was there, if you overlook something, if you make a transcription error when you're actually writing something down. Even though it has no material significance, once again, the adversarial court system, they're wanting to win points, and if they can get your evidence thrown out because you wrote down item number 23 instead of item number 32 and cast reasonable doubt, then the attorney will do that. The attorney is just doing their job. So your job as a forensic scientist is to make sure you don't make those sort of errors. Okay, where can you get the evidence from? Pretty much evidence recovery can be obtained from anything that you touch at all, like you're going to transfer your fingerprints immediately if you touch it. Anything that has contact with body fluid, anything that you wear, because from that you will get skin cells sloughed off onto items, which are often useful. And the other type of thing that crime scene examiners always look for is anything that is out of place at the scene. One of the most important things that they look for is a point of entry, and the first thing that they will normally do is check to see whether or not there was any damage at that point of entry, and they will take castings of that damage from door jambs and from the door itself, and they will then compare the marks on the physical marks on the door and door jamb at the scene back to test marks from a tool. And from that, if you happen to have that tool present in your toolbox and it matches up with the marks on the door or the door jamb, then there could be some questions that you need to answer. Having said that, just because you happen to find a tool in somebody's toolbox that matches the marks at the scene, it doesn't necessarily mean that they committed the crime. It would depend on how common is the tool, how many of those are around, was there any transfer of perhaps taint from a door jamb back onto the tool. That would be a two-way transfer, and then the evidence would be more significant in that case. The next couple of shots in this presentation show the type of evidence that we typically pick up. This is a photograph of a beer glass that was jammed into somebody's eye. This one, what we'd be looking for is not so much the blood on the glass, because obviously it was shoved into the victim's eye, so therefore it wouldn't be very surprising if we actually found the victim's blood on the glass. But you notice that the glass is broken, So what we would be looking for is to see whether or not there was any spatter back from the glass and whether that glass ended up on the perpetrator's clothing. So we'll be matching up the container glass with glass found on the suspect's clothing. The other thing that you can have happen, if there is blood on an item, if somebody holds it, they're going to get a transfer print from their own hands from the blood that's on the glass, and they'll be examining that for fingerprints. Pretty much this is the proper way to actually have a photograph taken of a piece of evidence. There's a case file number down there. This was just for forensic Canberra. It came out of the Federal Police. That was the case for the year 2408, and the -2 is just item 2, so we know that that's the second item that was picked up in the case. And there's always a scale. There's a centimetre scale, metric scale. And the reason that you want that is inevitably, if you don't have that in court, somebody always asks you, how big was it? So the easiest way is to make sure you've got everything in the photo, and then you don't have to worry about it. The next couple of photos are actually not taken that way. This would be something else that is exceedingly useful to pick up. Quite often you'll have people holding up various service stations, like there's been a rash of that going on at the moment. What you always hope for when that happens is that they will discard some item of clothing. If they discard the item of clothing, then you can actually DNA type the item of clothing, and then they're automatically put up into the national database. This here is a knife. This is probably reasonably topical at the moment from the Amanda Knox case. This is not the Amanda Knox case knife. This is just a knife out of my kitchen cupboard. But with a knife, if somebody has been stabbed, that is a great piece of evidence because you've got two ends of the knife. You've got the blade end, and what you're looking for is DNA or blood from the victim. And then the handle end, what you're looking for is DNA or fingerprints from the suspect. Usually you're not going to have very good fingerprints on a wooden handled knife, but you will have DNA. The downside of all of that is it depends on where you actually found the knife. Now, if you found the knife in the suspect's house, then the significance of DNA on the handle would not mean a whole lot because obviously they're going to be using knives in their own house. However, if you found the victim's blood on a knife in the suspect's house and the victim had not been in the house, then that would be a question that would need to be answered. One of the best sources of evidence is anything that you can put in your mouth. The reason being that saliva has a fair amount of DNA, not from the saliva itself, but from the cheek cells that are actually sloughed off and drop into the saliva. Saliva will have more DNA than blood, so it's a really great source for actually detecting, DNA on discarded items. So anything like cigarette butts, soda cans, drink bottles, anything like that. Sometimes we don't actually have items. What we actually have is victims themselves. There is another whole field known as disaster victim identification. 9/11 is a good example of that, where these techniques were employed. There can be mass disasters pretty much anywhere, anything that involves transportation, for example. In Australia, we actually had a couple of bus crashes, and we had to actually identify victims from the bus crash. Usually what you will try to do first up, there's usually a process that you go through. The first is visual. If you can ID somebody visually, that's great, or if you can get a family member. Sometimes that's not possible. Sometimes the damage to the victim is so great that you're not able to recognise them. Other times what you will use is clothing. If they have something that's very distinctive, that will also help. Also jewellery. One of the things that we found when we were examining bus crashes up in Grafton in New South Wales and Australia was that jewellery was actually very useful. Unfortunately, what people try to do, they try to be very helpful. They're quite often concerned about the jewellery being on a deceased person, and they want to take it off for safekeeping or whatever. That's a very bad thing to do. because we actually use that jewellery to identify the person. So we always say to people, don't touch anything until the person's actually been identified, and then we take care of their belongings. One of the other things that you quite often look for is birthmarks, scars, anything like that, or tattoos. Tattoos are absolutely wonderful. If somebody has a unique tattoo, which hopefully this is coming up, you can see that. It looks like I think a woodstock. Hopefully you can see that. That's an unusual one. And this one is a memorial tattoo. So when you're actually out on holidays, if you're going to know that you're ever going to have to do a forensic presentation, you should just wander up to random people who have tattoos and ask them, would you mind, would they mind if you took a photograph? Actually, surprisingly, most people like this person was quite okay about it. So I'm sure they're probably that he doesn't know that he's now blazoned across campuses nationwide, but this is the type of tattoo that is exceedingly useful for when you actually want to identify somebody. This one actually has signatures on it. It would be very unusual that you'd have two people with that same tattoo. The other type of things that are useful for identification are fingerprints, assuming that the person still has their hands intact, fingers haven't been removed, and dental records. This next one shows a scan of a dental chart. You can see that there's quite a lot of dental work done on this, and each of these individual marks, which you can see over here, are going to be unique to that person's dental records. So you can actually take that and x-ray the person and then compare your deceased victim along with their dental records. And then finally, if you don't have any of that, then you go to DNA. And the reason that you leave the DNA last is that it's probably the most expensive and the most time-consuming. And if you can do things in a simple manner, then you use the simple technique first. Okay, so what you actually have with DNA, this one is actually a shot of myself and my brother, and I would say you can have the personality or you can have the profile. So most normal people have on their desk, family photographs like this. Actually, on my desk at work, I have DNA profiles of my family members. So I guess that's kind of like the geeky thing that scientists do. Okay, so first, before you actually even get to that point where you're doing the analysis, the exhibits actually have to come in somewhere. And they normally come in through an exhibit reference area. This is the Forensic Services Division front counter of the Australian Federal Police. All exhibits that come through the scientific lab come through this area. They are all booked in, all tagged, all identified so that we don't lose them. Losing exhibits is very bad for your career. You should never lose an exhibit. Nowadays, we've actually got RFID, which is radio frequency identification. This is actually a great technique. There are two types of little tags. What you can do is you can insert these tags onto the proximal packages of your exhibits, depending on the type of exhibit that you're looking at. The advantage of these is you've got two different types of tags. You can have an active tag and a passive tag. Now, an active tag is actually battery assisted, but it has a short life. The passive tag is actually better. It's got a long life. One of the advantages of these things is that the data that is linked through these tags is all linked into your information management system. So you can actually update the data on the item as it's going along. This is much better than a barcode. Obviously, a barcode is a barcode is a barcode. Once it's on, it's on. There's nothing you can do about it. This you can alter. The other advantage of this thing is that you don't need a direct line of sight to actually know where that particular tag is. So for things where if you're doing things like, say, a drug importation case, usually think about the penalty of the crime. For drug importation, the penalties are very severe. So the greater the severity of the crime, usually the better the attorney. The better the attorney, the more questions they ask. The more questions they ask, the more documentation you need. So for things like drug importation cases where you need to track every movement of the drug from the exhibit bay to the examination bench, back to the exhibit bay, back out to fingerprints, back into the examination area again, back out to the exhibit bay. Any of those tracking, if you have this technology and you have those tags on your exhibits, just walking through an area, the information management system will pick up where that exhibit is at all times. So you don't need to handwrite notes as to where you're going. The system automatically knows it. The other advantage of having that type of system is that you don't have the transcription errors. So if you have a transcription error, remember that that can create reasonable doubt and the case can get thrown out. Okay, so you can also have barcode readers, which are useful for field items when you're actually collecting out in the field. So you can tag everything in the field and then record it with this device. Once you've actually got all your items tagged, bagged, and recorded, then you come to the first phase in the lab, which is actually searching in the lab. In the old days, this photo was probably taken, I think, probably 1999, 2000, around that sort of time period. You'll notice there's a pair of sneakers on the examination table, and you'll notice that they're festooned with little paper tags. The reason that you actually have to tag everything is that in court you have to be able to identify it. And if you've covered, let's say you do on average 100 cases a year, let's say each case takes, I don't know, a minimum of say 5 items, that's 500 pieces of evidence that you have examined over the year. Court case normally doesn't come around until 2 years down the track. You are not going to remember what the heck it was that you examined. So you've got to have some means of identification. So what we were doing in Australia was just using the regular old tags, like the clothing tags, and getting a tag gun and just tagging all our items this way. And it would have our signature on it, case number, item number, and the date that we actually examined it. So then all we'd have to do is pull the item out of the bag in court. Yes, that was the item I examined. Okay, once you've done that, then you've got to go through a screening process. Obviously, if you think about doing a DNA sample probably takes something about the size of a pinhead. So you imagine if you have a large item to examine, like a bed sheet, you need to narrow down what actual area you're going to target for examination. One of the fastest ways that we can do this is with something known as a polylight or an alternate light source. You shine light of various wavelengths onto the item, and either it absorbs much darker than the background, and so you can see the contrast. For example, I think it's 425 nanometers for blood. It will look like very dark black. Or if you're looking for something like semen, it actually fluoresces. And this is the one time, I know I said we never worked in the dark. We don't, except for when we're doing a polylight screen. And you can see here, you turn the lights off and you can actually see fluorescence coming back off the item. Once you've done your polylight screen, then the first thing you have to do is some chemical screening tests before you go to all the expensive DNA. So for things like sexual assaults, usually they'll use something that will measure a substance that is in high concentration in semen. The particular substance of interest is something known as acid phosphatase. It's an enzyme. And they will normally screen that, and if semen is present with the chemical screening test, you'll end up with a pinkish purplish stain. The other thing that they actually look at is not only things like blood and semen and saliva, but also the presence of hair, anything like that. They'd also pick that up and note where that was. You also want to know about any damage, or you also need to do a stain interpretation as well. So, for example, if something were heavily stained with blood, you might expect that that was some type of slow drip. If something had very fine spatters on it, then you would expect that to be an impact as a result of an impact. So from that, depending on the size of the stains and the type of the stains and where they are, you can give an indication as to what might have occurred. Usually, more often than not, it's a matter of saying what didn't happen rather than what did. We also complete all our screening tests, identify, do a species identification. This is particularly important if you're doing anything that involves a knife. Pretty much you test for anything that you could eat or anything that's domestic or anything that would be on the road. In Australia, we actually use anti-kangaroo blood because we do actually have a lot of kangaroos, particularly in Canberra, and on occasions we hit them. So you want to make sure that if you have blood on the bumper of the car and somebody says, I hit a kangaroo, that you're able to prove, yes, indeed, they did in fact hit the kangaroo and it wasn't a person. Back in the old days, we used to do serology where we'd look at protein markers, and then finally we're off and running and do the DNA. Now the DNA is relatively easy to do and relatively straightforward. First thing you have to do is you extract it. Notice, nice light lab, nice and bright so we can see what we're doing. Then you work out how much DNA is present. Then you do something known as an amplification, where an amplification is actually where you make multiple copies of the DNA of interest. When you're actually copying that DNA, you're not copying the entire genome. All you're doing is copying a tiny fragment. What you have is a couple of primers that bind to each strand of your DNA once your DNA is heated up. Those primers elongate to make copy, and the process repeats over and over again. And what you end up with is an exponential amplification, which the whole purpose of which is so that you have sufficient DNA that you can actually put in a genetic analyzer, and hey presto, you end up with a profile. You'll notice on this next slide, the top three panels are actually known as physical ladders. They are made up of many, many people within the population so that you have a range of where those markers might be. And I'm wondering if there's, oh great, it does turn up. So you can see there's sort of groups here. You can see there's one group here. This is the range for this particular marker group of interest. Then there's a second group, that's another set of markers. Followed by another group, that is another set of markers. In this case, what we're specifically changing is primers. The primers are the small fragments of DNA that actually bind to your DNA to give you that multiple amounts of DNA. The other interesting thing in this is this area over here, you can see that there are two peaks. This is melogenin. What you've got here is an X for your X chromosome and a Y, which is your Y. So in this case, this would be your XY. The advantage of this is that you can tell immediately whether or not your DNA has come from a male or a female. We've got a close-up of, Okay, Houston, we have a problem. Maybe it didn't like the position. Okay, this next one we've actually got a close-up, and you can see here is your melogenin marker. This one has the two peaks, so it's the X and the Y. So this DNA sample came from a male. This only has the one X peak, so this DNA sample came from a female. Okay. This was probably one of the greatest helps with respect to crime scene solving. DNA, the nuclear DNA, is one of the most powerful techniques. We're capable of using very small amounts of sample. It's got a great discrimination factor. We're pretty much able to almost individualize DNA right down to the individual, with the exception of identical twins. There are other types of DNA that are actually used in the forensic science lab. One is actually the good old human Y chromosome. This I actually took from a presentation for a colleague of mine, a guy by the name of John Butler, who has actually done a lot of work on the Y chromosome. And here you can actually see that we have our X and our tiny weeny little Y chromosome. This next slide, with apologies to the gentleman in the audience, this was set up with assistance from his wife. His wife actually helps John write books, and she decided that he needed to add a few extra traits into the Y chromosome. because obviously he irritates his wife on a regular basis with all these various traits, which I thought was quite amusing. So I included that one today. Okay. When we actually look at the Y chromosome, what we're looking at is all the markers are actually coming off that one single chromosome. Now, this is very different compared to nuclear DNA testing. With nuclear DNA testing, what you're looking at is a number of different chromosomes. The significance of that is that with nuclear DNA testing, you can take a characteristic from, say, chromosome 22 and get a frequency of occurrence, and then you can multiply that frequency of occurrence by how common a characteristic is from chromosome 4. When you're looking at Y chromosomes, because they're all on the one chromosome, they're all linked, so you cannot multiply any of those characteristics. Everything is inherited as one block. So the ability to discriminate is not as great. However, on the flip side, if we look at how Y chromosomes are actually passed down from generation to generation, we can actually make use of them. If you look at this next slide, what we've got here on the left is this autosomal pattern. What that means is a child is going to inherit half their DNA from mum and half from dad. So they're going to have a composite, which is why your brothers and sisters, don't all have the same DNA profile, with the exception of identical twins. With Y chromosomes, obviously Y chromosomes, only males are going to have Y chromosomes. So the Y chromosome is passed down from grandfather to father to son. So everybody who is in that paternal lineage line, they are all going to have the same Y DNA type. The other side is mitochondrial DNA, which I will get to a little bit later. And that is actually passed down on the maternal side. Okay, so if we have a look at, why this might be useful, like a Y chromosome, why it might be useful, it actually allows us to identify people in cases of missing persons cases. So say, for example, we found some remains and it was a male. We can actually look at the Y markers, and if we've got mum and dad present, we can compare back the Y marker directly to dad, and we can compare back the autosomal markers back to mum and to dad, and so that we can get a good feel as to whether or not this unknown male is actually a child of these two individuals. If we don't happen to have, say, the father, for example, say he's deceased, we can still do the Y marker comparison, because obviously this guy, this father, is going to pass his Y DNA to his son, but he's also going to have inherited his Y DNA from his father. So that means this missing father might have a brother. That brother will have the same Y marker. So chromosome from the uncle, and compare it back to the missing person, and you can check that way. And if you didn't have an uncle, you could also go up through the family tree, back down, and hopefully find some other male relative, a distant relative, and be able to compare the DNA that way. I'll skip this one for a moment. Okay. Male DNA, one of the other advantages of looking at the Y chromosome is that you are able to determine how many contributors have actually contributed to a stain. Usually with nuclear DNA, the maximum number of contributors you could probably identify in a stain is around 2 or 3. Once you get more than 2 or 3 people's DNA in a mix, it's very, very difficult to individualize it. And the reason being is that with nuclear DNA, what you're looking for is 1 or 2 markers per region of interest. So if this is the region of interest here, usually with nuclear DNA, you'll have either 1 or 2 peaks. So if you see 3 peaks in a region, you automatically know with nuclear DNA, I've got at least 2 people. You could also have 3 people though. With Y DNA, at every region, with the exception of one, but with pretty much every other region, there is only one band per region. So if you've got one band, that's one person. Two bands, two people. Three bands, three people. So you can tell immediately. The other advantage is with male to female mixtures. Usually the rule of thumb is if you have 1 part of person A, 20 parts of person B, you will only detect person B's DNA if you're looking at nuclear markers. If you're looking at male-female mixes and you're looking at Y markers, clearly females don't have any Y chromosomes, so no Y DNA. So you can have a 200-fold excess of female DNA in a male mixture, and you will always pick up the male, which is exceedingly useful for sexual assaults. Okay, let's move on to mitochondrial DNA. Most of the DNA that we've dealt with to date is coming from the nucleus, and inside the cell you also have these little powerhouses known as mitochondria. Mitochondrial DNA is actually maternally inherited, and although you have 2 copies of nuclear DNA per cell, with mitochondria, because you have so many more mitochondria in the cell over nuclei, you can have, in excess of 1,000 copies of mitochondrial DNA. It is maternally inherited. The downside of that means that all siblings are going to have the same DNA, so hence the "it was my brother" defense does work very well for mitochondrial typing. It's not unique to an individual, but it's exceedingly useful when you have very degraded samples. Because you've got such a high copy number, the likelihood of you having sufficient present to be able to detect the DNA is much greater. Mitochondrial DNA was what they actually used to a large extent for 9/11 victims because of the severe burning. Okay, one of the most famous cases where they've actually looked at mitochondrial DNA was the identification of the Romanovs. What they were actually able to do was use mitochondrial DNA to type those of the Tsarina, and in order to determine whether or not the children and the Tsarina were who they thought they were, they actually had to find a maternal relative in order to get a current maternal sequence of the mitochondrial DNA. So what they did was they went back through the royal family, and they were actually able to get a sample from Prince Philip, Duke of Edinburgh, who was actually related on the maternal line. From that, if they looked at Prince Philip's mitochondrial DNA, it was the same as the mitochondrial DNA detected in the remains, so they could say, yes, okay, the remains were in fact related to the royal line. In order to determine whether or not the Tsar was the Tsar, they had to utilise a maternal line of mitochondrial DNA from his family, and they were able to trace down through history until they finally found somebody and link it back that way. So you can see with mitochondrial DNA, although it is limited, it can be very useful if you are dealing with degraded remains. The downside of this also is that it is exceedingly expensive. Instead of just having, normally for a nuclear reaction, you'll have 1 tube per sample. For mitochondria, you may have 4 to 8 separate reactions that you need to set up. There are screening tests available. They're known as linear array. Basically what you do is you do a mitochondrial examination or amplification, and then you blot it onto a membrane, and you get one of these little strips, and you can see that there are different blue lines. You can see here that there's quite differences here between the pattern and number of blue lines for each of the regions, and from that you can basically determine whether or not you've got the same sample or a different sample. This is just another slide. You can see quite different. The reason that you'd want to do this is that to do this test, probably costs, I don't know, maybe about $30 in reagents per strip, whereas to do a sequencing reaction, usually the going rate is around, anywhere from $350 to $1,000 a sample. So for police agencies. Usually that's the cheaper way to do the screening first and then do the full-blown sequencing. With all sort of tests like this for mitochondrial typing, you always want to set up your evidence versus your reference samples, your separate batches so that you don't have any contamination. And then once you've done that, you'll do your full-blown sequencing, which actually looks somewhat like this. Okay, DNA typing, although that is what I've spent most of my time doing for my 20-odd years in the forensic area, there are actually other types of evidence which are at times more useful and more discriminating. You notice through this talk I've been saying that DNA will individualise with the exception of identical twins. One of the better pieces of evidence is actually fingerprints. Fingerprints you are able to discriminate between identical twins. The reason being that the fingerprints actually form on the fetus when it's actually developing in utero, and identical twins actually have different fingerprints. With a fingerprint examiner, what they basically do, like for many forensic systems, is they do actually look at individual characteristics and the whole picture. So this, I thought, was a great slide where if you look at these two examples here, looking at either the letter or the number in the middle, is it a number or is it a letter? It's all relative. It depends on where it sits according to the whole. For most forensic examinations, you're not only looking at individual patterns, but you're looking at the pattern as a whole to tell a story. With fingerprints, what they're looking at is different. Usually they're looking for things like bifurcations, crossovers, loops, swirls. They will normally classify those prints, and then from then, those prints go across to an expert for a better identification. Nowadays, they're actually looking at metal deposition on fingerprints to actually detect things that typically don't hold fingerprints well. One of the best things that they've actually developed is a method to detect fingerprints on cartridge cases and pipe bombs. So you can imagine with a cartridge case or a pipe bomb, it's going to be exposed to high heat. And for this particular method, what they're looking at is a change in the electrical potential between the metal surface and any of those inorganic salts that are coming out of your fingers and being deposited onto that metal surface. Other techniques, they will quite often bookend things, so they will use dyes with fluorescent tags and X-ray analysis. This particular technique detects things like sodium, potassium, chloride ions, any of those type of things that you'd expect to be seen coming out in sweat. Okay, so finally, I just want to go through a few cases. One of the best things that they've actually got now, they're starting to look at biometrics, and it's really useful in fraud cases. For biometrics, what they do is use a computer to actually scan across the face and get a 3D map. And what they can then do is, when you go to the ATM, there's always a camera, or more often than not, there's a camera. What they can do is they can take that video feed from the camera and scan that through and then scan it against mugshots. Now, normally if you had to go through mugshots and do it by eye, you can imagine how long it would take. Using the computer-generated facial recognition systems, they have managed to speed that up enormously. One of the cases I wanted to tell you about was a hit-run case with a kangaroo. Usually in Australia, we like to kid people when they come over. We like to tell them that there's lots of kangaroos running around in the street, which isn't true except if you're in Canberra. In Canberra, we do actually have kangaroos. And one dark night, we had, as is often the case, a group of people. They were having a party, and one of the guys had way too much to drink. And as often the case where alcohol is involved, he decided that he would get into an argument with his brother. And the net result was that he was so annoyed with his brother that he decided that he was going to walk home, which was good. At least he wasn't driving home, but he decided he was going to walk home. The problem was that the walk was from Canberra to Cooma, which is about a 2-hour drive by car down an interstate. So, dumb. And, of course, it was Canberra and it was winter, so it was cold. Also dumb, because if you've been drinking alcohol, obviously you're going to have constriction of your capillaries and you are not going to fare too well. So off he went. And when he was walking down, unfortunately, he walked down a very dark street and he was hit by a car. And usually, same thing like kangaroos and people, you get hit by a car, you don't fare too well. Unfortunately, he died at the scene. And the driver of the car decided not to stop. Just hit and run, took off. Unfortunately for the driver of the car, but fortunately for the deceased relatives and for the police, there was a guy following and he saw the accident. And he was a great witness in that he was able to describe the make of the car, the model of the car, the colour of the car. In Canberra, there's only about 300,000 people, so it doesn't take too long to narrow down when you've got a really good description of the car. Unfortunately for the police, the reason that our star witness knew all these details about the car was that he was one of the local vehicle thieves. And so he had a very good, extensive knowledge of cars. But when you've got somebody like that, they're not going to stand up well in court. So our job was to try and track down this car and get it back. Eventually, we tracked the car down, and when the driver of the car was interviewed, he claimed that he had hit a kangaroo, which actually in Australia is kind of like, well, maybe. And he said, I was sure I hit a kangaroo. I didn't think it was a person. I was pretty sure. But unfortunately for the suspect, when we recovered the car, we found him busily trying to scrub out stains on the front of the car. So that was strike number one. Strike number two is when you actually hit somebody with your car, the paint is actually remarkably soft. And our deceased person had jeans on, and when the car impacted with the guy's legs, we actually got a fabric pattern on the paint of the car. We were able to match that up with the fabric that the guy was actually wearing. So that was strike number two. And finally, strike number three was that when he was cleaning his car, he didn't clean it that well because he managed to forget blood that was caught up inside around the headlights. And we were able to get a minuscule amount of that and type that blood back to the deceased. And so the guy ended up going to jail. So I'd always say whenever you commit a crime, it's probably a good idea to just stop and own up to it because you're going to come unstuck down the track. One of the other bizarre things that happens at crime scenes is that for whatever reason, when people commit crimes, they're hungry. And I don't know what it is, but they go to the fridge, and they get the carton of milk or juice and chug the juice and then put it back in the fridge, We've found things like half-eaten apple cores and got a DNA profile from it. A colleague of mine in Western Australia had a ham sandwich. They managed to get, why you take a bite out and put it back, I don't know, but there was a bite taken out and we could get the DNA type from that. So if you're thinking of committing any crimes, don't touch anything and don't eat anything. And if you eat it, don't leave it behind. Okay, the final one that I want to go over, final case, was gunshot residue. This was actually a case of somebody coming up with a plausible excuse as to why they might have gunshot residue on their hands. There's a couple of ways that you can get gunshot residue on your hand. You can get it from handling a firearm. You can get it from being in close proximity to a firearm. One of the things that used to worry me was when I was working for the Federal Police, we had an armoury downstairs next to the lab, and they were also the guys that made Perspex boxes for electrophoresis units and fixed anything that was broken in the lab, and they had a full set of tools, so if you needed to fix a lab tap or something like that, you'd go in there. The problem with doing that is that because they were working with guns and gunshot residue, you'd quite often have, you could run the risk of actually getting that on your hands. And I used to have a backpack that, I'd cut around with me. And that was the same backpack that I used to take when I'd come overseas. So I was always somewhat concerned that if I were going through the iron scan here in the United States, that it would ping. Fortunately, it was okay and it never did. However, you can actually get transfer of gunshot residue onto you or onto your belongings. In this particular case, the victim, the deceased, was a landlord, and he had been shot in an apartment around the 8th of December in 2007. The suspect was actually a guy who had been evicted the day before, and the suspect was actually a construction worker. And the normal sort of thing for police, if there has been a gunshot involved, usually what they want to do is check your hands, check your clothing, see whether much you've got any gunshot residue on you. So needless to say, that's what they did. They took swabs of the suspect, and lo and behold, they found that he did have some sort of primer residue on his hands. His excuse for this was that he was in construction, and you can actually get those powder-actuated guns called a Hilton gun for, nailing in nails into concrete and things like that. And so his excuse was that the reason that he had the primer residue on him was a result of his job, and that's where it had come from. What you can actually do is you can do a scanning electron microscopy of various residues, and you can see, for these particular cases here, you can see that this trace does not look anything like that. So what the police did was they compared the gunshot residue that had come from the projectiles, the type of gun that would have fired the projectiles that were in the deceased, and compared that back to the powder attenuated Hildy gun, and they could see that two profiles are totally different, and therefore the story was bogus. Okay, I think that's, given the time, that is probably all we have time for at the moment. If you have any questions, I'd be happy to answer them now or come up after, and I'd certainly answer them then.
Great questions for Dr. Julie Sutton.
I was wondering on the DNA if you had a child that was being carried by a surrogate mother,